Okay, guys, so in a similar manner, I would like for us to find A inverse of this particular matrix using the Cayley-Hamilton theorem. So first of all, we're going to start by finding the characteristic equation of A and then finding A inverse. So the characteristic equation of A is given by, so evaluating the characteristic equation, we have 4 minus lambda, 3, 1, 2, 1 minus lambda minus 2, 1, 2, 1 minus lambda is equal to 0. So we go on to evaluate the determinant. Now taking 4 minus lambda, delete the row and column in which 4 minus lambda lies in, and then get the determinant of the small matrix left. So that will be 1 minus lambda multiplied with another 1 minus lambda, okay, minus 4. So that will be plus 4. Then taking minus 3, the position here is minus, comes with a minus, so minus 3. Delete the row and column in which it lies in, then get the determinant of the small matrix formed there. So that will be 2 minus 2 lambda minus, so minus 2. So that will be plus 2. Then finally taking plus 1, delete the row and column in which 1 lies in, and then get the determinant of that small matrix formed. So that will be 4 minus 1 minus lambda. And this is equal to 0. So we simply, let's open this up and see what exactly it gives us. So here we have 4 minus lambda, and then inside the bracket 1 minus lambda, that will give 1 minus 2 lambda plus lambda squared plus 4. Minus 3, then we have 2 minus 2 lambda, that will give 4. So we'll just have minus 2 lambda plus 4 over there, then plus 1 into 4 minus 1. So 4 minus 1, we can just write that as 3. 4 minus 1, which will just give us 3. 4 minus 1, 3, and then minus lambda, that will be plus lambda is equal to 0. Okay, simplifying this, we will have, so opening this up with 4. So let's see, 4. So even this and this, we should have just written it as 5. So like instead of having this and this, I can just have plus 5. Okay, now let's open up this bracket here with the 4. So we will have minus 8 lambda plus 4 lambda squared plus 20. Let's open it with minus lambda. Minus will give me plus 2 lambda squared minus lambda cubed minus 5 lambda. We are here now. Minus will give me plus 6 lambda minus 12 plus 3 plus lambda is equal to 0. Okay, so taking the like terms and then just putting the like terms together, we'll have, let's start with minus lambda cubed, then plus lambda squared. We have this and we have this, that is 6 lambda squared, minus values of lambda minus 8, values of lambda minus 5. Okay, so minus 5 plus 6 will give me 1. 1 from minus 8 will give me 7. Minus 7, so that will give me minus 6 lambda. And then the constants, we have 20, and then 20 minus, let's see, we have 20, and what else? We have 20 minus 12. 20 minus 12 is 8. 8 plus 3 is 11. So plus 11 is equal to 0. According to the Cayley-Hamilton theorem, matrix A satisfies its own characteristic equation. So I first of all want to write it with this value being positive. So I can have this as lambda cubed minus 6 lambda squared plus 6 lambda minus 11 is equal to 0, just so that it looks much better. So this will translate to a cubed minus 6a squared plus 6a minus 11 is equal to 0, according to Cayley Hamilton theorem. Now on to getting a inverse. In order for us to get inverse, then we will do that by pre-multiplying with a inverse on both sides. So pre-multiply a inverse is equal to what? We will pre-multiply this equation with a inverse on both sides. So that will give us a inverse into a 6a squared plus 6a minus 11 identity. Okay, so there's identity there, is equal to a inverse multiplied with 0. So what does that translate to? That will give us a squared, if you open the bracket, minus 6a plus 6 identity minus 11 a inverse. So minus 11 a inverse is equal to 0. Let's make a inverse the subject of the formula. So we will have a inverse is equal to 1 over 11. A inverse is equal to 1 over 11 into a squared minus 6a plus 6 identity. And what we want to get is obviously a inverse. So we will start by getting a squared, 6a, and then put all this together. So a inverse will be equal to, so let's start by getting a squared. So what is a squared? Our a, so our a was equal to 431 2 1 minus 2 1 2 1. So a squared will basically be this. You multiply by another a, 431 2 1 minus 2 1 2 1. Okay, so carrying that out, we will have our answer as, so for this position, we will have, that is first row, first column, first row, first column. So that is 16 plus 6 plus 1. So 16 plus 6 plus 1, that will give us 16 plus 6. So that will give us 22 plus 1, that will give us 23. Okay. The next one, so first row, second column, first row, second column, so that will be 12 plus 3, that will be 15, 15 plus 2, that will be 17. So if you do the rest in a similar manner, you will have this as minus 1, 8, 3 minus 2, 9, 7 minus 2. That will be our value for a squared. And then next is 6a. So 6a is basically multiplying by 6 the value of a. So that will give us, so we can just have minus 6a so that we add, or just have 6a, we will subtract. So 6a is 24, 18, 6, 12, 6 minus 12, 6, 12, 6. That's the value of our 6a. And finally, so finally 6 identity. So 6 identity. So we are taking this here, we are subtracting this. Let's first of all do that. So a squared minus 6 minus 6a plus 6 identity. 6 identity will just be, let's write it over here. So 6 identity will obviously be 6 multiplied by the identity. So that will be 6, 0, 0, 0, 6, 0, and 0, 0, 6. Okay, so if we evaluate this, a squared is this, and then we are subtracting this, and then we are adding this. What are we going to get? So let's do that for the first term. So 23 minus 24, that will give us -1, -1 plus 6, that will give us 5. Same for the rest of the values. Here we have 17. So 17 minus 18, that will give us -1, -1 plus 0, that will give us -1. So doing the same for all the other positions, we'll have here -7, we will have here -4, we will have here 3, 10, 3, -5, -2. Now remember our answer for A inverse. We said that A inverse is equal to 1 over the 11 of that. So our A inverse will be equal to 1 over 11 into 5 minus 1 minus 7 minus 4, 3, 10, 3 minus 5 minus 2. Okay, so this is our A inverse. Okay, finally, last example, we have our A is equal to, so this is example number 3, A is equal to 2, 1, 1, 0, 1, 0, 1, 1, 2. This is the value of our A. So we are told to find the characteristic equation of the matrix A, verify Cayley-Hamilton theorem, verify Cayley-Hamilton theorem. So find the characteristic equation and hence verify Cayley-Hamilton theorem. Okay, starting off to find the characteristic equation. So this is what we are going to have: 2 minus lambda 1, 1, 0, 1 minus lambda 0, 1, 1, 2 minus lambda. Determinant is equal to 0. Okay, fine. Evaluating for the determinant, you take 2 minus lambda. 2 minus lambda. Delete the row and column in which 2 minus lambda lies in. Find the matrix of the, find the determinant of the small matrix formed there, -0, -1. Delete the row and column in which -1 lies in. This will give us 0, -0. So that will give 2 minus lambda. So we have -1 into 0. Because if we delete this and this will give 0, this will give 0. So that just basically gives 0 plus 1. Delete the row and column in which this lies in. That will be 0, 0 minus. So 0 minus 1 minus lambda. So that will be plus. Lambda is equal to 0. Okay, so evaluating this basically simplifies to, if you evaluate this, you will get lambda cubed minus 5 lambda squared plus 7 lambda minus 3 is equal to 0. Cayley-Hamilton theorem says that a square matrix satisfies its own characteristic equation. So we'll have this as plus 7a minus 3 identity is equal to 0. So in order for us to verify, we just want to prove that this equation right here is satisfied. So we're going to look for a cubed, a squared, a replace here and prove that we are getting 0, 0. So what is a cubed? So in order for us to get a cubed is the same as a squared multiplied with a. So we are going to have a squared and then we multiply with a. So first of all, let's start by getting the value of our a squared. So a squared will be matrix A being multiplied 2 times. So we have our matrix A as 2, 1, 1, 0, 1, 0, 1, 1, 2. Multiplied by matrix A again, 2, 1, 1, 0, 1, 0, 1, 1, 2. This will give us a squared. So if you evaluate this correctly, a squared, we are going to get 5, 4, 4, 0, 1, 0, 4, 4, 5. It's row against column. Like if we, for this position, row 1 against column 1, that is 2, 2, 4, 1, 0, 1, 1. So 4 plus 1, 5, and so on. After getting the value of a squared, then we take a squared and multiply it with a. So a squared multiplied with a, that will be 5, 4, 4, 0, 1, 0, 4, 4, 5, multiplied with the value of a, which is 2, 1, 1, 0, 1, 0, 1, 1, 2. Okay, fine. So if we evaluate that correctly, we should be able to get 14, 13, 13, 0, 1, 0, 13, 13, 14 as our value of a cubed. So in a similar manner, let's continue and evaluate 5a squared. So we already have our value. So 5a squared, we already have our value for a squared as this here. So if we multiply that by 5 to get 5a squared, so that will basically give us, so 5a squared, that will be 25, 5, 20, 20, that will be 0, 5, 0, and multiplying with 5 here, 20, 20, 25. That's 5a squared. And then finally, so finally we have 7a. So just taking 7, multiplying with a. So 7a is basically equal to 14, 7, 7, 0, 7, 0, 7, 7, 4, 14, because this is like the value of a. And finally, minus 3 identity. So 3 identity is basically equal to 3, 0, 0, 0, 3, 0, 0, 0, 3. So if you put all that together, we are supposed to verify that a cubed minus 5a squared plus 7a minus 3 identity is equal to 0. If you put all that together, like let's just do maybe the first entity. So we have a cubed. So our a cubed in the first position is 14. So 14 minus 5a squared, 14 minus 25 plus 14 minus 3. That obviously gives us 14 minus 25 plus 14 minus 3. So 14 plus 14 will give us 28. 28 minus 25 will give us 3. 3 minus 3 will give us 0. So if you do the rest, you will find that this value here will give us 0, 0, 0, 0, 0, 0, 0, 0, 0, which basically proves. So if we show that this is equal to 0, then we've been able to verify the Cayley-Hamilton theorem.